Hello everybody, back to part 2 of our lecture. So we were talking now about heat transfer. And so the idea is with combustion, we've got our fire to ignite, we got our fire to burn, we know how it's going to burn, but now how does heat go from one place to another? How does the fire continue to burn? Like if you have the fire start in the grass, how does the fire go from the grass to the trees, to the log on the ground, to the shrub? How does all that happen? And so it happens by a process called heat transfer. It's also how the food in our ovens cooks. So it's the process or mechanism by which the energy is moved from one source to another. And in terms of heat transfer for us, there is going to be 3 methods that we focus on, and well, there just are 3 methods: convection, conduction, and radiation. And so we can see this basic kind of campfire example of convection, where if we're up above it, we can feel the heat being transferred. Radiation, if we're near it, we can feel the heat being transferred. And conduction, there's something that actually gets the heat transferred to it, and then that thing will have heat on it as well. And we can kind of see the same thing happening here through radiation and through conduction and through convection. Okay, so the presence of a heat source does not mean fire will start. You need everything to kind of be happening and everything to work out in terms of the fire triangle. Heat, though, must then be transferred to the fuel, and if the fire wants to grow, it's got to continually transfer heat from fuel to fuel to fuel, from the fuel that's on fire to unburned fuel. And then we know that will happen through that combustion process of dehydrating, and then the volatilizing of the gases, and then the burning of the fuel. And so our 3 methods are conduction, convection, and radiation. So let's go over those individually. So the first one we're going to focus on is back it up. Scoot myself over out of the way. There we go. So the first one we're going to focus on is conduction. And so conduction right here, that's transfer of heat by molecular activity from one part of a substance to another part of a substance. Or let's just be simple about it. It's transferring the heat by one thing touching the other thing. So when you throw a log on the fire, right, eventually that log will become too hot for you to touch, because that log is getting the heat. It's directly touching the heat, and that's why it'll get hot. The easiest example for a lot of people to think about is if you do something like you cook with a pan, a metal pan or a cast iron pan. Eventually you won't be able to touch that pan because the pan will get hot. And so that's what we're talking about when we're talking about heat transfer through conduction. And so what the example I wrote here, heat moves from the branches to the center of the log, then down to the soil. And so the idea down here is what is getting heat transfer from conduction. The soil is getting heat transfer from conduction. The branches or piece of log is getting heat transfer by conduction. This stump right here is getting heat transfer by conduction. All of that's getting heat transfer by conduction because it's actually touching the heat. It's actually touching another substance that has heat, that is on fire. Now in terms of convection, that's when we feel heat up above. So that's transfer of heat by the movement in a gas or a liquid, and that's usually what's happening in the smoke plume. And so if we feel heat above a campfire, or you have heat in a smoke plume, that could even shoot off firebrands, which are embers that may ignite spot fires, that is convection. So when the heat's transferring by liquid or gas, and that's usually, then because heat rises, that's the convection heat. So if you have a convection oven, what's happening in a convection oven is that heat is rising, but then there's a fan in there, so it's going to take that heat that rises, and then it's going to circulate that air. So it's going to use that air and use that heat that's coming out in the air above the above the thing that you're cooking, and it's going to kind of circle it back in and help it cook some more. The third part is radiation. So radiation is heat transferred via electromagnetic waves that travel at the speed of light. Now that sounds fancy, but really all we're saying is radiation like convection. You do not need direct contact. So conduction is heat transfer with direct contact, whereas radiation and convection, there is no direct contact in terms of heat transfer. So with radiation, that's where you're standing near something, but you still feel the heat. So like a car radiator, or back when houses used to have radiators, you would always get close to it because you wanted to feel the heat, but you don't want to actually touch it because it's really hot. And so radiation, the easiest thing to think about is a campfire. And you put yourself near the fire, but you never put yourself right on top of the fire because you can feel that radiant heat. So you just want to go close enough to get that radiant heat. So with this heat transfer now, how does fire spread? So what you could have happen is you could have direct contact. So we get this wind-driven fire. We got unburned fuel here, and our fire moves in and it has direct contact with it. We go through the whole combustion process and we get heat transfer through conduction. We can also get some heat transfer happening through radiation. So maybe our fire's here and we get radiant heat starting that preheating phase over here, and then these spot fires are able, or these embers are able to spot over here and then catch this unburned fuel on fire. This one, we get the wind, or really a wind-driven fire. So all of this convective heat that's up here, now that convective heat is being pushed here, and now that convective heat plus this one, so we got conduction happening here, we got convection happening here, and we got radiation, because we always have, if it's a fire, there's always radiant heat. Same thing happening here. We got our conduction happening. We might have, because it's uphill, if we get this wind, maybe we get a little bit of the convection heating happening, and then we have our radiant heat happening as well. And so then I think that takes us, so we've talked about heat in terms of heat transfer. We've talked about oxygen and the role that oxygen plays in terms of the fire triangle, and the fact that since we have 21% oxygen in our atmosphere, there's always oxygen available. So then what's left and what becomes a real focal point in terms of the fire triangle, in terms of understanding fire and how to manage and try and control fire, is the idea of fuel. And what do we know about fuel, and how can we understand fuel better to be able to try and eliminate fuel as much as possible, to try and stop fire. And so fuel characteristics strongly affect the rate of combustion, so how quickly the fire can kind of destroy everything, and heat transfer, how fast it can move and how much fuel it can take. And then moisture plays a huge role into this, and I think we all kind of understand that that the drier the fuel, the more rapid combustion you have, but the wetter the fuel, the less chance there is for combustion. If everything is snow covered, we don't really worry too much about fire because we've got that moisture, everything's wet and it's cold. But what we really worry about here in California is things get hot, and if we have a drought, things get really dry. And when they're hot and they're dry, combustion can happen really easily, and it can happen quickly. But what other characteristics will affect the way fire spreads? One of the ones to focus on is fuel load. So the fuel load is defined as the amount of fuel available for combustion. So when we're talking about fuel load, we're talking about it being able to affect the spread and intensity. So if we look at this figure here on the right, so we've got light fuels, we got heavy fuels, we got uniform fuels, and we got patchy fuels. So the idea that when we think about fuel load, is there a lot of stuff to burn or is there little stuff to burn? And so one thing to think about is fires like in California, we get a lot of lightning in the Sierra Nevada mountains, and we get a lot of lightning in the southeastern deserts. but we don't really worry about the fire in the southeastern deserts as much. And the reason we don't worry about fire in the deserts is because there's not that much available fuel. It's definitely light fuels available in the desert. Whereas if there's if it's hot and dry in the Sierra Nevada mountains, there's a lot of dead trees from bark beetle kill. There's a lot of fuels cut from invasive plants. There's a lot of just this overabundance of fuels because we don't have that decomposition process, and we haven't been logging or doing some other sort of disturbance to get rid of those fuels. So in the Sierra Nevadas, we end up with heavy fuels, and that's why we can have some of the big mega fires that we've had this last year. Also, the fuels are pretty uniform. In the Sierra Nevadas right now, you'll see something that looks much more like this than you will see something that looks like figure 4 with the patchy fuels in the open space. Because if you have that discontinuity, those spaces in between, that makes it harder for the fire to be able to keep going and keep finding fuel and fuel and fuel and fuel to keep that keep building that energy. Other things that are going to become important in terms of fuel load: size, class, packing ratio, and the idea of dead or alive, or really the idea of moisture in the fuel. So surface to volume ratio, or really what we're trying to talk about, is the size of the fuel particle. So fuel coarseness is a function of fuel particle size. So the smaller the size of the fuel particle, the greater ratio of surface area to volume. So the more surface area available for heat transfer and combustion, the quicker the fuel is dried and heated. So what does that mean? So if we take these examples right here, this has large surface area, this has small surface area per volume. And so so the smaller the fuel particle, the greater surface area you have. So what does that mean? It's when you have a great surface area, things can dry out very easily because they'll get that radiant energy from the sun. They dry out very easily. It means they're going to be more available and more ready to go. So grasses and these fine fuels that we talked about earlier, grass, conifer needles, twigs, things like that, those things are going to dry out real quick because they have more surface area, and because they're going to dry out more quick, they're going to be ready to, they'll go through the preheating phase faster, and they will catch fire a lot easier. The way to really think about this is, how do you start a fire? You don't go, well, here's the biggest log I have, I'm just going to hold the flame to it and wait for it to catch fire. No, you're going to say, okay, I got a couple big logs. Well, let me put those in like a TP formation. And then underneath that, I'm going to put all this small stuff, all these little twigs and needles and whatever, newspaper or whatever I got. I'm going to light that on fire and let that convective heat and that radiation and then somewhat of that conduction actually build that fire in there. Packing ratio. So the proportion of the fuel bed filled with fuel. So when we're talking about packing ratio, we're talking about fuel bed compactness. So if the packing ratio is too high, not enough oxygen can reach the fuel and combustion cannot occur. So when we're talking about packing ratio, what I really want you to think about is the idea of this graphic that I have here at the bottom, then also that campfire example. So if fuels are next to each other, it's easier for fire to transfer from one place to another. If it's separated like this, it's much harder because it takes much more effort, much more heat, much more oxygen to be able to pull that fire along. Whereas if the fuels are all right next to each other, that's not that hard. So if you think about the forest, everybody says, well, the forest is overcrowded these days. Well, why is that a problem? And it's a problem because your fuels are concentrated. You've got that compactness where it's easy to go from one tree to a shrub, to grasses, to another tree, to another tree, to another tree, instead of it being separated and patchy like we talked about on the earlier slide. The other part about it is the way that the fuels are organized. So it talks about here the need to allow air fuel into the fuel, but not too much. So going back to our campfire example that we've been using a couple times, why do you put the logs in a TP formation, right? It's because you want the fuels to be touching and you want them to be close to each other, but you also want to leave space for air and for oxygen to be able to get in there, because you know you need fuel, heat, and oxygen to be able to make this work. If you just stacked them all up in a big pile, yeah, it might catch fire, but you're going to have to take much more effort, put much more heat, probably put a whole bunch of lighter fluid and all this other stuff to try and make that burn. Whereas if you kind of can arrange your fuels in a certain way, it's going to be easier. And so it's really becomes problematic with the idea of if you get a wind-driven fire, because, fire might not be so bad, but if you get the wind blowing, so you get that high amount of airflow, if you can get high amount of airflow and you get high heat, and you've got then like a forest that's overcrowded, then we start seeing these mega fires. And that's why people get really worried during the times where they talk about the Santa Ana winds coming in, because it's a hot wind, and it's a hot wind blowing fast. It's usually during the dry and hot time of the year. And if you get a spark, you end up with just a huge fire because of this idea of the packing ratio, the idea that your fuels will be concentrated, they'll get that airflow that they need, and it's just kind of all the right conditions for fire to burn. Your live fuel moisture. So that is the ratio of the weight of water versus divided by the dry weight. So basically, you weigh the fuel. You would basically weigh the fuel as it is. Then you would oven dry the fuel and then weigh that. And then you would divide the one by the other to figure out how much water or how much moisture is in the fuel. And the reason you'd want to know this is because the moisture in herbaceous fuels respond really, really well to changes in relative humidity. So we're talking about herbaceous fuels there. So we're talking about grasses and forbs, all those little fine fuels with a large surface area to volume ratios, the ones that can change and dry out really quickly. So in studying the moisture, you find out that they respond a lot to changes in relative humidity. So that's why when we talk about weather, one of the things we're going to focus on is not only temperature, but relative humidity. So how moist the air is, because we know that the live fuel moisture in herbaceous fuels will change and respond quickly to changes in relative humidity. Woody fuels will hold water a lot longer. Most of the time, annual plants can lose all of their moisture by midsummer. That's why for us here in California, fire season kind of really kicks off. Like we really start worrying like August, September. That time tends to be really bad because that's when everything is usually dried out by. Perennial plants can hold moisture through the fire season, but late fall, they usually end up losing their moisture. And that's become a big deal lately because the fire season has kind of been extended a lot longer than it used to be. So now we start seeing fires in like October and November, sometimes where that didn't used to be a thing, but that's because, these perennial plants, that's when they're losing their moisture, and we're still seeing those high temperatures and not getting that cold snap and not getting that moisture that we need in the late fall. There's an inverse relationship with age. So in terms of your fuel moisture, you got lots of moisture in your fuels when they are younger. As they get older, they lose less and less. That's why it's an inverse relationship. So as you get older, you get less water. If it was a positive relationship, you get more water as you get older, but they hold less water as they get older. So if your fuel is older, it becomes more flammable. So these older forests that we have, the fuel they'll be able to hold less water. So as they age, they get more and more flammable. Some conifer trees and some shrubs have waxy cuticles, and that's an evolution or an adaptation, and it's an adaptation to prevent moisture loss, because they know that's as they get older, that'll become problematic in their perennial plants. So they adapted to have these waxy cuticles on the leaves that will help prevent moisture loss. And so here's just an example of live fuel moistures at a specific site. And so here it's looking at two types of chaparral. So we're looking at shrubs, two different types of shrubs, and there's a 60% critical threshold for live fuel moisture. So if it goes below 60%, that's when it would be an available fuel to catch fire. And you can see during that this, because it's a perennial plant, it's that late fall, it's late summer to late fall is when it kind of has its time where it can be really problematic in terms of fuel moisture content. And so we really don't want to see fires from August to December. But if we do end up getting fires in this type of fuel in August to September, we wouldn't be surprised, because that's when it's lacking in terms of its fuel moisture. And so also going and looking at the fuel bed properties. So where would we be more likely to see flaming combustion as opposed to smoldering combustion? Well, if it's dry, if it's loosely packed, and if it's small stuff, we're likely to see flaming combustion, because things will burn quicker, so we can get to that gaseous phase and get kind of moving a lot quicker. Whereas if things are moist, so there's a little bit of moisture in there, or there's a lot of moisture in there, if it's densely packed, so you need much more heat to get something to burn, so it can't move as fast. And if you've got large size particles, you're going to see more likely smoldering than you will see flaming combustion, because it can't move that fast, because it's got to keep going, spending a lot of energy in that preheating phase and in that gaseous phase to be able to get stuff to be ready to catch fire. And that takes us to the idea of time lag classes. So in terms of, because we know moisture content is so important, we wanted to come up with size classes for the fuels, and we wanted to incorporate the idea of moisture. And so the time lag classes, when we're talking about time lag, what we're talking about is the proportion of a fuel particle that contains moisture being a primary determinant of fire behavior. And so dead fuels usually range from 0 to 35% fuel moisture. For that perennial plant that we just looked at before, it said anything below 60% is problematic. And that's so 60%, that's where it starts to really become problematic, but still alive. If it was 35% or below, it'd be a dead fuel, just, ready to burn. So these size classes are going to be kind of separated by their time lag. So you keep hearing me say time lag. What does that mean? So time lag means, the definition of time lag is how long it takes a fuel to lose or gain moisture to be in equilibrium with the moisture in the air. And so what we're talking about is, if you read the exact definition of time lag, it's how long it takes a fuel to lose 63% of its moisture to equal the moisture in the air. And you go, 63%, what does that mean? And it's just about this idea that how long does it take for the moisture in the fuel to be the same as the moisture of the air, of the outside temperature. So if you had, let's say you had a clump of grass in your hand, how long would it take that clump of grass as the day goes on and it gets hotter to be the same moisture content as just the air? And so this is the idea. I've got this graphic up here of time lag. So here's our initial moisture content. This is the moisture of the air. How long is it going to take for the moisture content in this to get down to here? That is our time lag. And so what we come up with is we have 1 hour fuels, 10 hour fuels, 100 hour fuels, 1,000 hour fuels, and 10,000 hour fuels as our kind of 4 or 5 categories, depending on how you want to look at it. I don't talk too much about 1,000 hour fuels or 10 hour or 10,000 hour fuels because the smaller stuff is kind of more important because it's the stuff that gets studied more. So 1 hour time lag fuels. So basically things that are 0 to 1/4 inch in diameter. So you're thinking conifer needles, you're thinking grasses, thinking small twigs. Those things take about an hour to lose enough moisture to be the same as the moisture of the air. It takes about an hour for those to dry out that way. The 10-hour fuels, so anything from 1/4 inch to 1 inch in diameter, that would take about 10 hours for that to happen. Anything from 1 inch to 3 inches in diameter, that would take 100 hours, 1,000 hours, 3 to 8 inches, and anything larger than 8 inches takes about 10,000 hours to equal the stuff in the air. And so if you look here on the right at this chart, it says fuel moisture content and hours of continuous precipitation. And you can see that when you get a lot of rain, right away, your 1-hour fuels and your 10-hour fuels, they get full of fuel moisture. Whereas it takes a while for your 100-hour fuels to gain moisture. So your 1-hour fuels and 10-hour fuels can gain and lose moisture quickly. Your 100-hour fuels, not so much. And so that's why you'll see a lot of focus on 1-hour fuels and 10-hour fuels. And so why do I say you'll see a lot of focus? Well, because with 1-hour fuels, they react rapidly to changes in relative humidity. So hour to hour changes. So when we're talking about if you're on a fire and you're fighting a fire, though the thing you really want to pay attention to is your fine dead fuel moisture or your 1-hour time lag fuels, because those ones are the ones that are going to change hourly. And so that would be needles, twigs, moss, lichens, small shrubs, and grasses all fit into that 1-hour category. You're also going to want to pay attention to your 10-hour fuels, because those can show day-to-day changes. So those are small branches and shrubs, and they'll show you day-to-day changes in terms of humidity and moisture content. Your 100-hour fuels, the trends there will be, they'll show you moisture trends of several days to several weeks, and 1,000-hour fuels will show you seasonal changes in moisture. 10,000-hour fuels don't really show you the changes as much. So it shows you here, it talks about a 10,000-hour fuel or large down logs that are solid or moderately decayed. So we're not going to learn that much in terms of moisture from those things. We'll learn much more about our moisture trends in terms of our 1-hour fuels that change right away, hour to hour, or 10-hour fuels that can change day to day, or our 100-hour fuels that can show us kind of the weekly trend or the, a couple days worth of trend. And that takes us then into the idea of fuel models. So we start off with the idea of fuel, and we know that that's going to be the one that we want to really pay attention to. And so how does it work? We've come up with these. We talked about fuel load, and we talked about surface to area ratio and size and time lag classes and all these other things. So we're going to put fuels then into fuel models, because we want to kind of categorize these things so that we can be able to start really thinking about, well, when we talk about this type of fuel, how's it going to work? How's it going to burn? What kind of fire could we expect if we're in this sort of a fuel? Like if it's all shrubs, or if it's mostly shrubs, or what if it's grasses with a few spread out trees? And so what happened was they decided to create fuel models to assess potential fire behavior, and they're still used by all the different agencies. I'm going to focus on the Forest Service right now. And if you click, you can pause the video right here, and you can click on the link right here. It's to a Forest Service publication that covers the different fuel models, the Scott and Bergen fuel models that are used currently by the Forest Service. And so there's 40 different models used right now. They're broken into 4 different categories. So grass, shrub, timber, and slash. And then the book does suggest that that there should also be a brush grass or a shrub grass model as well. And so if you look right here, This says SH2, so this is in the shrub category, and it's a moderate load dry climate shrub. And it says the primary carrier of fire in SH2 is woody shrubs and shrub litter. It's a moderate fuel load, so it's higher than SH1. Depth to about 1 foot, no grass fuel present, spread rate is low, flame length is low. So because we're able to separate out into these 40 different fuel models, we can kind of start having an idea of what kind of burning conditions we could expect, or what kind of fuels they should look like. And then also that starts to give you the idea of, you know, does this place look the way it's supposed to? So it says right here, if you have this, if you work in this area and it's an SH2, it says there's no grass fuel present. So if you start to see large patches of grass in this area, you might be like, hey, this is not supposed to have grass, but it does have grass. And it starts kind of giving you a base to work from, to really start to understand and adapt to the area that you're in and be more prepared when it comes to understanding what fire might do in your area. And so this is, I don't, just in case we're worried, I do not expect you to memorize all the different fuel models. I do definitely want you to understand that it's 40 fuel models, and it's broken down into 4 groups, into the grass, the shrub, the timber, and the slash. Definitely should know that, but I don't expect you to know all 40 groups. I'm just going to kind of give you an overview. So these are the grass fuel types, so you'll see them with the GR abbreviation here, and then there are 9 in here, as well as 2 other ones, which are the grass shrub, because they're GS as opposed to the GR. And so it also breaks it down into this idea of, well, if it's short grass, if it's timber grass in the understory, or if it's tall grass. And you can see, so like GR1 and GR2 are definitely about short grass, whereas there is no tall grass if you're looking at GR1 and GR2. And if you look through that that booklet that I attached to it, you'll see that these all come with pictures, and they all come with graphs to kind of explain it. So here's the graph with rate of spread and flame length. And so you can kind of see, like, all right, so if I'm in GR1 or I'm in GR2 or I'm in GR7, what should I expect if the wind speed picks up? And so in terms of flame lengths, what kind of flame length should I expect if the wind picks up? And you can see, like, if the wind picks up, even if you're in GR1, because it's short grass, no big deal if the wind's blowing fast and the wind's not blowing as much. Whereas if you're in GR9, where you've got tall grass and the wind picks up, that can get really bad. And so we start kind of, with these fuel models, we start having this base to work from where we can understand things. So going on to our shrub fuel types, which we looked at an example of, we looked at SH2. So you can see we've got all these shrub fuel types, 9 of them, and then we also got TU5, timber understory 5, and we also got grass shrub 2 as well. And you can see it's broken down into chaparral, which is shrubs type seen on the California coast and in Southern California. Brush, so just a bunch of different types of shrubs. Dormant brush, and then southern rough. So southern rough is stuff particular to the southeastern United States. Some nasty kind of plants that I spent a lot of time dealing with, and some stuff that it's waxy and it's volatile and it can catch fire pretty quick. The other explanation, let me go back a little bit. So you'll see these comparisons here, and it says 1, 2, 3, and it says 4, 5, 6, 7. So there used to be 13 specific fuel models, but then it got updated to 40 to break it down a little bit more. And so the comparison here is these ones up here, those are the older fuel models, and then these ones down here on the right are the newer 40 fuel models. And I'm sure they're working on updating the fuel models even more. Again, so we did the grass fuel type, the shrub fuel type, the timber fuel type. You can see they've got 9 of the timber timber litter, and then they've got 5 of the timber understory and 1 of the shrub ones as well. And so you've got compact timber litter, hardwood timber litter, and timber understory from the original set. And then the last one is the slash field type. So if you're not comfortable with what we mean by the word slash, that's the idea of all the stuff that just ends up on the ground. So if you're in a forest and there's a lot of blowdown, or if you're in the forest and there was a logging project, or if you're just in an older forest with a lot of dead and down woody fuel, you know, you go walking through the forest and you've got to step over logs and you're always hearing branches cracking underneath your feet. That's slash. Whenever there's a lot of stuff on the ground, that's slash. And so we've got timber 1, we've got a couple of the slash, or 4 of the different slash models, and you can see that there were 3 different slash models in the older set. And you can see, just for comparison, we looked at the grass rate of spread and flame length graphics. So for these slash models, for the slash model, I can't remember specifically which slash model we picked, but you can see that they break it down with dead fuel moisture. So you can see if there's very low and low fuel moisture, right away you get some wind, it's problematic. If you got high fuel moisture, it's still pretty problematic. And you're still, if you get a lot of wind, you can see in a slash sort of setting, wind is very important. And that makes sense if you think about it, because if we got a bunch of dead stuff on the ground, if we get a lot of wind, then we can get that fire and that heat, and it'll burn through that stuff. If we don't get a lot of wind, it won't necessarily be much of a problem. You can see under 5 miles an hour, you're not going to expect much to happen in terms of fire. But as soon as you get over 5 miles an hour, as soon as you get enough oxygen with that heat, it can become very problematic in terms of slash.